All right, so today we're going to be doing lesson 3.2 on postulates and algebraic proofs. So before we get started, I just have a couple of properties to go through with you. And so most of these are going to be some that are familiar that you'll remember from algebra. Some of them may be new, but we'll get to there. So first is called the reflexive property. The reflexive property is just one term. It's when a term is equal to itself. So when you're using the reflexive property, it's going to be like for every number, A is equal to A. That could be like when you're solving an equation and you get that the answer is all real numbers, and at the bottom you get 5 equals 5. Okay, so that's the reflexive property. Something is equal to itself. Okay. All right, the next one is going to be the symmetric property. The symmetric property has two terms, and it says if the two sides of an equation are switched around. So it says for all numbers A and B, if A equals B, then B equals A. So an example you might see of that is, say you're solving an equation and you get x equals 7, but the person next to you gets 7 equals x. Those are the same thing, and switching the order of that around is just called the symmetric property. And the last one, if you have three terms, is called the transitive property. The transitive property says for all numbers A, B, and C, if A equals B and B equals C, then A equals C. So ultimately the thing to know here is that you can skip the middle term in the conclusion. What I mean by that is you'll notice that A is equal to B, and then it says B is equal to C. So that repeats itself, so you can more or less mark that out. It's gone, and you're left with A equals C. Okay, so that's the transitive property. All right, a couple more. So on this slide, we're talking about addition, subtraction, multiplication, and division. So you'll notice here they are. It says if A equals B, then A plus C equals B plus C. So on all of them, you'll notice the only difference is we added C or subtracted C, multiplied C, or divided C. But you'll notice on all of them, it happens on both sides. So in order for you to use one of these four properties, the operation has to happen on both sides of the equation. That kind of reminds me of when you first learn to solve an equation, if you're trying to isolate the variable and you have to say like subtract 7 from both sides. You do it on both sides. You do it on the left side, you do it on the right side as well. Okay, a couple more. Substitution property. I think you've probably heard of this one. Maybe you just didn't know this was what it was called. But it says for all numbers A and B, if A equals B, then A can be replaced by B in any equation or expression. So that would be like if you're solving an equation and it says the angle 1 is equal to 2x plus 3. And then you work it out and you get that x is 4. So if you wanted to know the actual measure of angle 1, you would go back and substitute in 4 everywhere you see an x. Okay, so that's the substitution property. Distributive property, for sure you know that one. When you see these parentheses like this, you distribute, multiply the A by both terms inside. And then the last one is combining like terms. Terms with variables are combined without moving anything across the equal sign. Combining like terms is different than addition. Because addition, you have to do the addition on both sides of the equal sign. Combining like terms happens without going across the equal sign. So that would be like if you had 7x plus 2x plus 4 equals 8, something like that. You have these like terms, they would add together, but notice nothing gets added on the other side. So all I've done is combine like terms. All right. So I've got a couple of examples for you. So this first one says, name the property of equality that justifies each statement. So 3x plus 7 equals x plus 12. Well, this is my last sticky note, and now it's not sticky. Sorry, guys. The struggle is real. Okay. All right. So 3x plus 7 equals 12. Then 3x equals 5. So when I work problems like this, I like to look at the beginning. This beginning part is called the given. It's your hypothesis. And I like to compare it to the end. The end is the conclusion. It's the stuff at the end. So it's just like English class. It's the conclusion. What do you notice is different from the hypothesis to the conclusion? So at first glance, I noticed it was 3x plus 7. Now it's just 3x. So I got rid of this plus 7. We know from algebra, our equation solving skills, that to move a plus 7 to the other side, you would have to subtract 7. And if you subtract 7 on one side, you have to do it on the other. And that would leave you with 3x equals 5. So since I've done subtraction on both sides of the equal sign, we can call that the subtraction property. All right, look at the next one. So the next one says if AB equals CD, again, that is your hypothesis, your given information, then AB plus EF equals CD plus EF. So that one was easier to see to me just because I read it immediately. I noticed that there was a plus EF added on both sides. Since I added something on both sides, we can call that the addition property. All right, last one of these. If PQ plus RS equals 18 and RS equals 8, then PQ plus 8 equals 18. So the given or the hypothesis on this one is longer. It's got two parts. And then my conclusion is just this last part back here. So immediately I noticed the RS is gone. It's been replaced with an 8. So remember, anytime you replace something with an equivalent value, we call it substitution property. All right, moving on. So I've got a couple of postulates for you. Postulate is a vocabulary word. Postulate is something that we accept to be true without proof. Another word for a postulate is an axiom. You'll see both of these words interchangeably. Okay. A theorem, on the other hand, has already been proven to be true, and it can be used to justify that other statements are true. So a theorem is going to be like the Pythagorean theorem. So forever ago, Pythagoras decided the Pythagorean theorem was a thing. He worked out all the kinks. He has this big, long proof showing you why and how it works. So it's already been proven to be true versus a postulate, something we accept to be true without the proof. So in geometry, we have what we call the first 7 postulates. So here it goes. Here's the first one. Through any 2 points, there's exactly one line. So you could reword that by saying 2 points determine a line. So we're going to call that postulate number 1. Any 2 points, I can draw one line. Okay, fair. I believe it. Number 2, through any 3 points not on the same plane, not on the same line, there's exactly one plane, meaning 3 non-collinear points determine a plane. We talked about that back in Unit 1. To name a plane, you have to have 3 points that are not on the same line. So again, I'm fine with that because I know to name a plane, I need 3 points that are not on the same line. All right, my third postulate, a line contains at least 2 points. Okay, so let's think about that for a second. A line can't just contain 1 point. I don't have anything to draw off of. I have to have at least 2, but I can have as many as I need. A line is just made up of an infinite number of points, but that second point is giving me direction. A plane contains at least 3 points not on the same line. So a plane has to have at least 3 points because if I just have 2, it's just a line. So I've got to have 3 to be able to put them all on a flat surface, on a plane. So that's postulate number 4. Number 5 says if 2 points lie in a plane, then the entire line containing the 2 points is also in the plane. I think that one makes good sense. I've got 2 points, they're in this plane, then the line that they're on is also in the plane. So don't forget that planes extend indefinitely in all directions. So like this plane is going on forever, so is this line. Okay. Postulate number 6, if 2 lines intersect, their intersection is exactly 1 point. That one, to me, is one of the easiest ones. What else would it be? 2 lines intersect, they're going to intersect to make 1 point. And then the last one, number 7, I have to think about this one a little bit more, but it says if 2 planes intersect, the intersection is a line. So the best example I can give you of this is to look around in the room you're currently in. Find you where 2 walls intersect. Okay, so there's my best attempt at some walls. Like let me try again. Here's the floor, and then we got this wall, and then we got this wall over here. It looks a little better. Okay, so here are my 2 planes, my 2 walls. Here's the floor. Those 2 walls, when they intersect, so when the 2 planes intersect, they form the corner, and that corner is a line. Okay, where the 2 walls and the floor intersect, so right here forms a point. Just there's an extra 10 cents for you for today. So where the 2 planes intersect is a line. All right, so here's a couple of examples for you. Determine whether each statement is sometimes, always, or never true. All right, so it says if plane T contains line EF and line EF contains point G, then plane T contains point G. So we've got a plane, and there's a line inside of the plane, EF. Then it says line EF has point G on it. Well, point G must be on plane T. That one is always true. All right, look at the next one. Line GH contains 3 non-collinear points. This is the line, non-collinear points. That doesn't even make sense. Points can't be non-collinear and be on the same line. So because of that, this one is going to be never true. Okay, and then the last one, if AB and HK are coplanar, then they intersect. So I've got these two lines, they are coplanar, then they must intersect. So let's think about this. Just because lines are on the same plane, does it mean that they will intersect? Maybe. Does it mean that they won't? Again, maybe not. So this one is going to be sometimes true because maybe they're parallel on the same plane, or maybe they do intersect. You never know. Okay? All right. Okay, so let's look at this. So this one says to state the postulate that can be used to show that the statement is true. So this one says that E, B, and R are coplanar. So I'm talking about 3 points forming a plane. So if I go back and look at my postulates, it says 3 non-collinear points determine a plane. That's postulate number 2. Okay, the next one, B, D, and W are collinear. So I'm talking about 3 points that are collinear. Since it's 3 points, I'm going to look at postulate number 3. A line contains at least 2 points, meaning it could contain 3 as well. So that's going to be postulate number 3. All right, a proof. Actually, I think that's where I'm going to stop. So I'm going to make a second video for this lesson about proofs. All right, see you later.